Alright, let's pick up where we left off on our camera obscura video. When the aperture becomes very thin, what effect does that have on the light that passes through? Now for this, we're going to use the exact same setup as we did before. But we're going to add this little diffraction screen. We're going to orient the box so that the covered aperture now directly faces the sun. Another thing we can do is to use a simple mirror so that we can redirect the light from the sun to the exact point where we need it to be. Now there's two ways that I learned to make the diffraction screen. Both of them require some cardstock and both of them require some tape. Now the first and easiest way to make this is to simply cut some pieces of tape off and tape this aperture down until you have a tiny slit. And don't be discouraged if it doesn't work the first time. I literally had to make about 10 of these to get that slit to be small enough. Another way we can do this is to cut out some foil, tape the foil to the cardstock, and then either use some scissors or an X-Acto knife, cut a very, very, very thin slit. And you'll get something that looks like this. And now let's put the slit over our aperture, point our box at the sun, and behold, look at this beautiful pattern we see. But what's going on here? How did we get from a single band of light like we had before to what we see now? These bands of light with some dark fringes in between and even some rainbow coloring in there. These are the questions we'll be exploring in this video. All right, in order to understand where this pattern that we're getting on our screen is coming from, we have to get a little bit into this concept of wave superposition. What happens when we combine waves together? How does that combination of waves behave compared to the waves that made it up? So let's start off with two sine waves. Now we have the red one and the blue one, and you'll notice that they are exactly the same. They have the same frequency, they have the same amplitude. There is no phase difference between them, which means that their peaks and their troughs line up. So the maxima and the minima all in exactly the same place. Now this purple wave is the combination of our red and blue waves. What I want you to notice here is that when we are at the maximum for the blue and the red wave, which is 1, the combination of those two waves is of course going to be 2 because we're adding 1 plus 1. We're adding the values of the two waves. And similarly down here, when we're at the minimum of the red and the blue wave, which is -1, the combination, the superposition of those two waves is going to have a value of -2. This phenomenon is called constructive interference, which means that the two waves are adding up to give you a greater value. And this happens when the maxima and the minima of the two waves that are adding up together are in sync. This is called being in phase. But what happens now when we change this blue wave and we shift it over by pi? Now we have two waves that are out of phase. So what happens when we get the superposition of these waves? When we add them together, we will see that they cancel each other out completely. They are always equal and opposite to each other. The combination of them in this case is always giving us a value of 0. This is called destructive interference, and it happens when the waves are out of phase. And here we have the case of complete destructive interference, and this happens when the phase difference between the two waves is half a wavelength, when they are going through opposite values at the same time. The wavelength of both of these waves is 2 pi, but there's a phase shift of pi between them, which is, of course, half a wavelength. Now that we've covered interference, we're ready to tackle the geometry of the diffraction setup. I don't know about y'all, but the first time I did this experiment, what I was expecting to see on this screen over here was just a bright band of light right here. That's all I expected to see. But that's not exactly what we saw, is it? What we saw was, yes, a bright band of light right in the middle. We saw places on the screen where we had these fringes of light. and different colored light at that. Why is this going on? The light is gonna hit our slit, and of course all the light that hits the cardboard is gonna get absorbed. None of it is gonna get into that box, but some of the light does go through that slit. And what we see is that instead of just following a straight path and giving us that central band and nothing else, what we see when this slit is narrow enough is that once the light hits that slit, it starts moving as a wave. And this is called diffraction, the spreading out of waves as they pass through an opening. The other central concept that we have to understand is Huygen's principle. What Huygen's principle tells us is that once we get this little wave here, every single point actually on this wavefront acts as its own source. We have actually infinitely many point sources on this wavefront. And what Huygens principle tells us is that every point on a wavefront acts as a source. So what we have here is pretty much waves traveling like this. So the line is the max, the space in between is the min. And we can start to kind of see, okay, maybe there's going to be some constructive and destructive interference as these waves propagate through the space and ultimately end up on our screen. And that's exactly what we're going to explore here. Where does that interference happen? Why do we get this specific pattern that we see here? And as I said, we can consider that this wavefront here, as it passes through, is going to have infinitely many sources, right? We're just going to draw 3, and I want to show you that that's really enough to understand what's going on here. We're going to take one at the top, right at the edge of where the slit is, and one right at the middle. And what we're going to need to analyze is how does the path difference of the light that goes from here and ultimately ends up at this point here on our screen differ from the light that starts off right in the middle and ultimately ends up at that same point. When we see these peaks, there's a maximum in the intensity of the light that's hitting the screen. And when we see these valleys, these are minimums. So let's zoom in here. And like I said, we are going to consider the path difference of these two. So what I'm going to do is I'm going to just draw us a straight line here, from the top to here. I'm saying that from there on, from this point forward, from here to here, and from here to here are the same distance, which means this little segment here is the path difference between the two wavefronts. So our delta x is our path difference between the top path and the middle path. And since this is a straight line, this right here is going to be a right angle. So I'm going to just redraw it up here. We have a right angle where one side is delta x. And if you notice, that other side is going to be half of the width of this. Remember, this is all together is w. So this is going to be w over 2. If we take a straight line from the middle and we call the angle that it makes with that middle path theta, if this distance d is big enough compared to our width, which it definitely is, because remember our width is probably a millimeter or 2, it's very, very tiny, then that angle theta is the same as this angle here. It's an approximation that we can use in this case. We have the opposite side to the angle and we have the hypotenuse, so let's just set up our sine equation. We know that sine of theta is opposite over hypotenuse, so delta x over w over 2. I'm going to go ahead and simplify that for us. Delta x equal to sine theta times w over 2. Now that we have an expression for our path difference, we've already talked about where destructive interference happens. We know that if there's destructive interference happening there, these waves must be out of phase. And not only that, we know that they must be out of phase by half a wavelength. So essentially what we know is that the path difference delta x must be lambda over 2, the wavelength over 2. We can go ahead and substitute that for delta x, and we know that this must be the condition for destructive interference. And now we can simplify this even further as the wavelength equal to sine theta times the width. If we rewrite this once more, that sine theta is equal to the wavelength over the width. Look at what this is saying. This is telling us that wherever we see destructive interference, that is dependent on these two variables. That is dependent on the wavelength. That is dependent on the width of our slit. So where this ratio is equal to the sine of that angle there, we are going to get these destructive interferences. So this tells us that any time that we have a multiple of the wavelength over the width, that is going to give us another minimum. This first minimum that we see here is n equals 1. The next one would be n equals 2. All these are going to give us those dark fringes where there is complete destructive interference. Yeah, okay, we covered these 2 points. There are infinitely many points that are acting as sources. So how come we're just disregarding those completely? We can just generalize. So we already know that this top point and the middle point completely destructively interfere right over here. But let's say we take the next one down from the top and the next one down from the middle. If we do the same analysis with these, we would still have the same path difference delta x because we move both points at the same difference. This would still be half the width. So we're going to get the exact same result. This result of lambda over the width equals sine theta for destructive interference still holds. And it works for the next pair of points and so on. Now, at this point, you're probably wondering, yeah, okay, kind of makes sense why we have the destructive interferences at those points. Well, why haven't you really talked about the constructive interference? Let's just tackle this central peak first. We know that the path difference when these waves are all traveling in a straight line to that center is going to be 0, which means they'll be in phase and interfere constructively. From there, finding the expressions that give the other order of the maxima are quite a bit more complicated than what we've done here, and so will not be in the scope of this video. Maybe I'll make another video explaining those. For now, knowing where the dark fringes are and the relationship between that position and the wavelength is enough to start to give us an idea of what's going on in this system. Now I want to bring your attention to this expression one more time, and specifically to the fact that it is dependent on lambda, the wavelength of the incident light on our slit. And though this expression is specifically used for complete destructive interference, we'll use it here to qualitatively explore how the wavelength affects the diffraction pattern and specifically the banding that we see. Now let's remember that we are working with sunlight here. And now sunlight is not just made up of one wavelength, it is made up of the full spectrum of visible light and therefore has many different wavelengths within it. On the high end of the wavelengths, we have red light, which is around 700 nanometers. And on the low end of the spectrum, we have violet light, which is around 400 nanometers. And we can already see that the higher the wavelength that gets put into this equation here, the higher the sine of that angle is going to be, meaning that we're going to have a greater diversion from our original angle to wherever we see a band. And therefore, if we put lower values of lambda into that equation, there should be a smaller diversion from the original path for the smaller wavelengths. And we can see that that's actually exactly what happens. So we can see these little red bands of light here and our violet bands of light around here. And we can clearly see that the wavelengths that were diverted most, that have a greater angle change from the center, are the larger wavelengths, which are the lowest energy wavelengths. And on the other hand, of course, the higher energy, lower wavelength light was diverted less from the center. And if we replicate this experiment with monochromatic light, like this laser here, we see that of course we don't have rainbow banding because all the light from this laser is the same red wavelength. So there you have it. Now we have a slightly better idea of why this interference pattern happens, what we call a diffraction pattern. And it shows us the difference between how light behaves at the macro scale when our aperture is pretty big relative to this slit. But now that we've narrowed this slit and forced the light to pass through a very, very tiny space, we see that light behaves a little bit differently. Now we start seeing how light behaves as a wave as well. And that is the beauty of the dual nature of light. It is both a particle and a wave at the same time. Like and subscribe for more. See y'all next time.